Hi everyone, this is Gennaro Vessio. I'm assistant professor at the Computational Intelligence Laboratory of the Computer Science Department, University of Bari. I'm going to present my joint work in collaboration with Professor Giovanna Castellano on deep convolutional embedding clustering for digital paintings with a case study on Picasso's artworks. Let's start with a brief context. As you perfectly know, our cultural heritage has an invaluable importance for the cultural, historic, and the economic growth of our society. It is of importance not only to art historians and museum curators, among the others, as would be traditionally the case, but also especially to computer scientists. In recent times, a large-scale digitization effort, in fact, has led to the increasing availability of large digitized visual art and fine art collection. A remarkable example includes the well-known WikiArt. This availability, along with the recent advances in computer vision and pattern recognition, has opened up new opportunities for computer science researchers to assist the art community with automated tools to help analyze and further understand visual arts. Among the various tasks which can benefit from the application of computer science techniques, we recall classification and categorization of digital paintings based on their visual style, and historical knowledge discovery to discover influences among different painting schools. Traditionally, to perform such tasks, art experts rely on their inherent aesthetic perceptions to find similarity relationships among paintings. Unfortunately, this perception, which can be also influenced by their subjective knowledge and experience, is first extremely hard to verbalize and conceptualize. Second, extremely difficult to translate into features and precise label to be assigned to digital paintings. Indeed, this label may be based on subjective evaluations. Our goal is to develop an automatic tool to group together digital paintings based on visual features, so on their visual appearance, and on an unsupervised approach which relaxes the constraints to have precise label of paintings. Unfortunately, applying traditional techniques to this complex domain presents a lot of drawbacks. First, applying traditional clustering algorithms like k-means may be unfeasible to the very high dimensionality of the raw pixel input space. Second, applying feature reduction techniques such as PCA can lead to ignore possible nonlinear relationship between the original input and the latent embedded feature space. Third, some other variants of k-means, in particular the spectral clustering, become computationally expensive as the data grows large. Finally, as previously mentioned, engineering meaningful features according to domain knowledge can be extremely hard. To overcome these limitations, we propose to use a refinement of the increasingly popular deep convolutional embedding clustering recently proposed by Guo and others. There are two main benefits related to using this technique. First, we can exploit the capability of deep learning models to find a nonlinear relationship between input and output data. Moreover, by using convolutional layers, we make the model even better suited to the specific image domain. In this slide, we can see an overall scheme of the proposed network. It is composed of a convolutional autoencoder, which learns to reconstruct the original input by compressing the pixel values into a much more compressed embedding space. and attached to this layer we can find a clustering layer which performs a soft clustering assignment. The reconstruction loss and the clustering loss are minimized simultaneously. I will not dive into details of this architecture as it is well known in the recent and current literatures, and details about the slight variation we made to make the model better suited to the specific domain can be found in the paper. Model training works in two phases. First, there is a pre-training of the convolutional autoencoder to learn the nonlinear mapping between the original feature space and the latent embedding space. Then, K cluster centroids are initialized by using the traditional k-means. A soft assignment is first computed between the embedding points at these initialized cluster centroids. An auxiliary target distribution aimed at improving this soft assignment is computing. Then a loss based on the Kullback-Leibler divergence between the soft assignment and the computed target distribution is calculated and minimized. As previously said, input reconstruction and clustering assignment are optimized jointly. To evaluate the effectiveness of the method in finding meaningful clusters, in particular within the production of the same artist, we performed a case study on a database collecting artworks made by a very popular artist, namely Pablo Picasso. We chose Picasso mainly because his artistic production was characterized by clearly recognizable stylistic periods. As for experimental setting, we resized and normalized the input images as is usually done. The autoencoder was pre-trained for 200 epochs by using the well-known Adamax optimizer. The overall network was trained by using the same optimizer and with a fixed threshold which stops training when a clustering assignment does not improve between consecutive iterations. As evaluation metric, we used well-known internal clustering criteria that are the silhouette score and the Kaliski-Arabax index. The silhouette score ranges between -1 and +1, with 0 indicating overlapping clusters. The Kaliski-Arabax index measured between and intra-dispersion of the obtained clusters and tends to grow numerically, so higher the better. This table shows the performance obtained by the method by varying the number of clusters from 2 to 6. The best partition is obtained with k equals 5, which obtained the highest silhouette score. We can see that the Kaliski-Arabax index tends to increase or decrease according to the previous measure. So the two scores agree upon the clustering obtained by the method. In any case, well, good values are obtained in all cases, regardless of the value chosen for k. As for a qualitative evaluation, we can observe, in the case of 5 clusters, that distinctive features have been looked at by the model to group paintings. A cluster is clearly related to the recognizable rose period of the author. A second cluster is clearly concerned with the so-called blue period. Another cluster mainly contains drawing, as the dataset we used does not only contain paintings. Finally, the other 2 clusters are clearly related to the very popular Cubist period of the author. We can observe that by varying the number of clusters, when this number is low, the method looks at macro stylistic features. So, for example, with k equals 2, the method separates between cubism, artworks, and all the other stuffs. Conversely, when K grows, the method starts looking at fine-grained features. So, concluding, preliminary encouraging results have been obtained, which confirm the effectiveness of the method in addressing these highly complex image domains. Future work will use much of the existing literature on Pablo Picasso to try to label paintings in order to perform a much more systematic evaluation based, for example, on external clustering criteria, so injecting some knowledge into this process. Finally, we can observe that layers learned by the first convolutional layers of the encoder path of the network can be analyzed to find out which were the distinctive objects in the paintings that led to their clustering. I have concluded. Thank you very much for your kind attention.